Before we dive into today's episode, make sure to hit that subscribe button. It's the best way to stay updated with our latest insights.
Ladies and gentlemen, welcome to the CTSS Academy podcast. The energy is electric. The crowd is alive. Let's dive into greatness. We're champions strong.
Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
I want you to picture something for a moment. You take a photo on your phone, you hit send, and then, just moments later, your friend who's miles away, maybe across the country, maybe across the ocean, they get that exact image, perfectly rendered, intact, and in the right order. Have you ever stopped to wonder about the silent, invisible architecture that makes that whole thing possible?
It really does feel like magic sometimes, but it's not. It's more like a highly organized bureaucracy. And that structure is what we call the TCP/IP model, Transmission Control Protocol, Internet Protocol. At its heart, its core purpose is, well, it's simple, but it's also revolutionary. It provides a standardized set of rules.
Rules for what, exactly?
For how devices connect to the Internet and how data is transmitted between them. It's all about creating a reliable, virtual communication network over these vast and often pretty unreliable physical distances.
That distinction feels really key: reliable communication over an unreliable physical layer. Okay, so our mission today is to do a deep dive into the design philosophy of this model. We're going to unpack the 4 conceptual layers of its architecture, explore the essential protocols that act as its common language, and try to understand why this specific framework, designed decades ago, became the absolute foundation of the modern internet.
To really get it, we should probably start with the foundational rules of TCP itself, the things that allowed it to succeed. The first critical rule is that it is a connection-oriented protocol. This isn't like, just yelling a message into the void and hoping for the best.
Right.
A digital handshake, or a session, has to be established between the sender and the receiver before any real data starts to flow.
So you establish a clear line of communication first. That seems vital for any kind of guaranteed delivery.
Exactly. Which brings us to the second point. Its inherent reliability. The physical internet can be a real mess. Packets get lost, they arrive out of order, or they get corrupted. TCP takes all that incoming data and makes sure that even if those digital bits arrive all jumbled up, they are put back into the correct original order before your application ever sees them.
And what about speed? I mean, if I'm sending a massive file, how does TCP stop my computer from just completely overwhelming a slower recipient?
That's the third point, and it's a clever one. Flow control. TCP is constantly monitoring the other end's capacity. If the receiver signals that its buffer is getting full, TCP just automatically throttles the sender's speed. The sender never overpowers the receiver. It keeps things smooth.
Okay, so connection-oriented, reliable, and it manages flow. And what was the last one?
Oh, right. Finally, it supports a really flexible architecture, which is the reason we can just keep plugging new systems and devices and entire networks into the internet without, breaking the whole thing.
Okay. Let's follow our photo through this system. So we can think of the TCP/IP model as, a factory with 4 distinct floors. Our data starts at the top and works its way down, getting packaged and addressed at each level until it finally hits the physical wire at the bottom.
And let's start at that bottom floor, which is where the rubber really hits the road. The network interface layer. Some people call it the network access layer. Its job is incredibly granular. We're talking about defining the actual mechanical and electrical details of how data should be sent.
So if I'm on Wi-Fi, it's handling the radio signals. If I'm plugged into a fiber optic cable, it's dealing with the pulses of light.
Precisely. It's responsible for encoding the raw ones and zeros onto the physical medium coaxial fiber, whatever. But here's the crucial limit. This layer only handles transmission between 2 devices on the same local network. It gets the data onto the wire, maybe to your local router, but it has no idea how to get it across the continent.
Right, so the moment our photo leaves my local Wi-Fi and needs to cross the city or the world, it has to move up a floor, up to the second pillar, the internet layer. And this is where the magic of global communication really happens, right? This is the routing layer.
Absolutely. The internet layer's main job, and this is all powered by the Internet Protocol, or IP, is to send packets from any network and any computer to the destination. It doesn't matter what winding route they take to get there. It's like the network's built-in GPS. It handles routing, assigns addresses, and just tries to get the packet going in the right general direction.
Okay, but hold on. We just said TCP is all about reliability, but you're saying this layer, the internet layer, doesn't actually promise reliability. Why would you design the foundational global routing system to be unreliable?
That is the critical insight into this whole architecture. The internet layer IP is designed to be minimalist and fast. That's it. If you try to bake in reliability, like guaranteeing every packet gets there in order, right at the routing level, you would just slow down every single piece of traffic everywhere. So IP is connectionless. It fires off packets. If a packet gets lost, the internet layer doesn't care. It's fast, it's efficient, but does not guarantee safe arrival.
So if the internet layer is just sort of pointing the way and hoping for the best, where does the reliability that we need for our perfect photo come back into the picture?
That is the job of the third pillar, the transport layer. This is the quality control department. It provides reliable data transport from a specific application process on your machine, say your messaging app, to the matching process on the destination machine. TCP is the famous protocol that lives here, and its whole job is basically to clean up IP's mess.
So our photo data, which was just blindly routed by the internet layer, now gets sorted out, it gets its segments numbered and everything.
Yes. The message from your app gets chopped into segments, each one gets a number, and they're sent down to the IP layer. Then, when the segments arrive at the other end, maybe out of order, maybe with some missing, the transport layer's job is to reassemble them, check for errors, and, this is the key part, send back acknowledgments. If an acknowledgement for a piece doesn't come back in time, TCP just assumes it got lost and sends it again. That constant checking and resending is what makes it reliable.
Wow, so it's creating order out of potential chaos. Okay, so finally, we get to the top floor, the one closest to us as users, the application layer. If the transport layer is the mailroom, the application layer must be the customer service desk.
Exactly. This is the highest level layer. It's interacting directly with your messaging program, your web browser, your email client. Its functions are things like identifying who you're talking to, synchronizing the data exchange, and checking if the server you need is even available.
And the examples here are the things we use every single day. File transfer with FTP, email with SMTP, and so on. It's the visible face of this entire, invisible architecture. So now that we've followed our photo through the 4 layers, let's talk about the specific languages, the protocols that define what is actually happening.
We have to start with the bedrock, IP, the Internet Protocol. As we said, it lives in the Internet layer. Its function is pure addressing and routing. Every device needs that unique numerical label, the IP address, to be found. Its routing function is literally what creates the Internet as a network of networks.
And its essential partner is the TCP part, the transmission control protocol in the transport layer.
TCP is the workhorse. It handles the session, the segmentation, the error checking, the reassembly.
Right.
IP gets the packet to the right city. TCP makes sure the entire message arrives safely at the right apartment, perfectly packaged. That combination is what creates that robust virtual connection.
And moving higher up the stack, we get to the protocols that define the services we actually use. I guess the most famous one is HTTP, the Hypertext Transfer Protocol.
Oh yeah, HTTP is the foundation of the World Wide Web. It's an application layer protocol for requesting and transferring web pages and all their resources, images, text, videos, from a server to your browser.
And then there's the most human-friendly protocol, which is probably DNS, the domain name system. I mean, without DNS, we'd all be carrying notebooks full of numbers.
It's the Internet's phone book, really. It lets you use memorable names like thedailydive.com instead of having to memorize a string of numbers. When you type that name, DNS just translates it into the IP address so the Internet layer knows where to send the packet.
And beyond those big ones, there's a whole list of specialized protocols doing specific jobs behind the scenes, right? Like SMTP for email.
Right, Simple Mail Transfer Protocol. That's what handles sending emails across servers.
Yeah.
We also have FTP, the File Transfer Protocol, for sending files between machines.
And there are a couple of older ones that are still really important for system administrators, like Telnet.
Terminal Network, yeah. It lets you log into a remote machine and use it as if you were sitting right there. And finally, SNMP. Simple Network Management Protocol. That's the framework that lets administrators monitor and manage all the routers, switches, and servers that make up the Internet. It's about keeping the system healthy.
That is a seriously powerful suite of languages. But, to really understand why TCP/IP is the one that dominates, we have to look at its competitor. Or maybe it's older, more theoretically perfect cousin, the OSI model.
This comparison is so important for context. TCP/IP came out of ARPANET. It was designed with practicality in mind, and crucially, this was before the internet exploded. The OSI model, on the other hand, was developed by the ISO after a lot of these networking protocols were already in place. It was meant to be, technically perfect.
And the structural difference is pretty stark. OSI, the Open Systems Interconnection model, it has 7 layers. It keeps a really meticulous separation between things like the physical, data link, session, and presentation layers. TCP/IP is just more pragmatic, right? It just mashes those functions into its 4 layers.
Exactly. OSI is what you might call a vertical approach. Very strict separation of duties. TCP/IP is more horizontal. It prioritizes ease of implementation over that theoretical perfection. And that pragmatic choice has trade-offs, of course.
Right, like the header size. Our sources mentioned that the minimum header for OSI is a tiny 5 bytes, but for TCP/IP, it's 20 bytes. That's 4 times bigger. Why did the network tolerate that kind of bulk? That extra data has to be sent with every single packet.
It tolerated it because those extra bytes bought a lot of functionality and, well, future-proofing. The larger header in IP provides way more options for flexible addressing, for fragmentation information, quality of service fields. It allowed for more optional data that helped TCP/IP adapt as the internet got more and more complex. It was a choice for flexibility over pure, raw efficiency.
So the extra bulk wasn't just noise, it was padding for future growth. That makes sense. And that helps explain why, despite its technical flaws compared to OSI's elegance, TCP/IP just won.
Precisely. Its victory was all about adaptability. It operates independently of the OS, it supports a ton of routing protocols, and its client-server architecture is just incredibly scalable. But maybe the most powerful thing was its focus on connecting different kinds of computers and networks. That cross-platform compatibility was everything for building a truly global network.
But every design has trade-offs. What are the costs of that complexity that administrators still deal with today?
Well, our sources are clear that it is complicated to set up and manage. And replacing a core protocol inside the stack is notoriously difficult because of how interconnected the layers are. Remember how TCP has to clean up after IP? That dependency makes it hard to just swap a component out.
And circling back to a point we touched on earlier, even though TCP is reliable, it's managing that reliability through hard work, not because it's an inherent guarantee. That transport layer, despite all its sequencing and acknowledgements, doesn't actually guarantee delivery in the model itself.
It doesn't. It only guarantees that if delivery fails, it will try again. If the network just keeps failing, the attempt will eventually time out. And that just reinforces the core principle. The reliability is a service built on top of a fundamentally unreliable but fast underlying network.
Okay, let's zoom out one last time. We've dissected the layers, network, interface, internet, transport, and application. We've followed the data through protocols like IP, HTTP, and DNS. We've seen how TCP/IP provides these reliable virtual connections across what are often very unreliable physical networks just by layering responsibility.
And we talked about how TCP/IP became the standard, even though it lacked the clean structure and had a bulkier header than the technically pristine OSI model. It won because it was pragmatic. And this raises a really important question for you, the learner, to think about. Given that TCP/IP was implemented before a perfect solution existed, how much does the real-world success of any technology really rely on its technical perfection versus its timing and its practical adaptability to the messy needs that already exist? What stands out to you as the most critical compromise the world accepted when we chose this foundational model?
Something fascinating to think about as you're browsing the web today. And if you want to dive deeper into mechanics of reliability, a great place to start is exploring the differences between connection-oriented protocols, like the TCP we discussed, and connectionless protocols, like UDP. Understanding those two approaches will unlock a whole new level of the internet's secrets.
Thanks for listening. If you found value in today's episode, please subscribe and leave us a review. It helps more people find the show. See you in the next one.
Hey, yo! Haven't you checked out our new book yet? Link in description.